Welcome, everybody. I'm Sarah Leroy. I'm the Science Communications Coordinator for the Southwest Climate Adaptation Science Center, or Southwest CASC. I'm just going to go over a few housekeeping items before I turn it over to Greg. There will be time for questions at the end of this webinar, so please put any questions you have in the Q&A window, and we will get to them at the end. This is the third webinar in our spring series. The first webinar was on Southwest CASC tribal-focused engagements and opportunities, and the second was on rebuilding forests after fire. The recordings for both of these are now on our website, and I will put the link in the chat window in just a minute. And this webinar is also being recorded and will be posted on Monday. When you leave the webinar today, you'll be directed to take just a very brief survey, and we would appreciate if you could take a minute to fill it out. And then lastly, I just wanted to mention for you to check out our recent Come Rain or Shine podcast that was posted on Wednesday, and this is on drought, snowpack, and streamflow, so very related to the topic of the webinar today. And we talked with Brad Udall from the Colorado State University and Adrian Harpold from the University of Nevada, Reno. We produced the podcast in collaboration with the USDA Southwest Climate Hub, and so I will put this link in the chat as well. Okay, so I think I am now turning it over to Steve Jackson, who is our federal, our USGS director. Steve, are you there?
Yes, my video is being blocked, I guess, but that's okay. It's my great pleasure to introduce Connie Woodhouse, who from the University of Arizona. Connie is, I would say, a climate adaptation science hero. In that she was one of the pioneers of deep engagement between climate science and stakeholders, particularly the water management community in the West. Connie is a climatologist and paleoclimatologist, and has been working very closely with those communities for several decades, centering on drought and related hydroclimate climate issues. Connie was recently appointed a Regents Professor at University of Arizona, a well-deserved distinction and a very highly honored one. So I will turn this over to Connie. We have been sponsoring some of her work from the Southwest CASC since the very beginning, back in 2012, and she's been showing us and people across the community the way forward for effective engagement of relevant science to pressing issues from our stakeholders. So off to you, Connie.
Thank you, Steve. Thanks for the nice introduction. I feel like I have a lot to live up to now with that kind of introduction. I will share my screen. And hopefully everybody can see that. I can't see you, so it's always the weird part. Someone let me know if you can't see it. Let me just put this up here so it's out of the way. Okay, so my talk is on a collaborative project, Plausible Scenarios for Future Colorado River Drought. Now, the genesis of this project actually it came directly out of the two projects that were funded by the Southwest CASC. The first was disentangling the influence of antecedent temperature and soil moisture on Colorado River water resources, and the second was anticipating future impacts on streamflow using multi-century climate records and applied hydrologic models. And both of these projects focused on the influence of temperature on streamflow in the upper Colorado River Basin. The research team for both of these projects included Greg Peterson, who's from USGS in Bozeman, Steph McAfee, and Adam Zank from University of Nevada, Reno, Greg McCabe from USGS in Denver, and Steve Gray from USGS in Alaska. So that was our research team. And then our partnering agencies evolved a little bit over the course of the two projects, but they included Bureau of Reclamation, the big federal water management agency in the Basin, Denver Water, the largest urban water provider in Colorado, Salt River Project, a large urban water and power provider in the Phoenix area, the Southern Nevada Water Authority, important water provider in the Las Vegas area, the Colorado River District, which is a Colorado Conservation River District, one of a number, but this one is focused on the Colorado River. And then the Colorado Basin River Forecast Center, which is one of NOAA's river basin forecast centers out of Salt Lake City. So those are the agencies. But of course, we didn't deal with the agencies. We partnered with and worked with the water managers themselves, real people. So these are some of the people of the community of practice with whom we collaborated. Not everybody, but just a few of the photos I could find. Now, this term community of practice was one that I came across fairly recently, but I think it really described our partnerships very well. A community of practice is a set of people that have shared interests and concerns and that engage in peer learning. And so this describes the water managers in the Upper Colorado River Basin, or the managers who use Upper Colorado River water. They interact with each other, they learn from each other. I had an interesting conversation with a colleague during a defense a couple of weeks ago, where she commented that she thought the Colorado River water managers didn't really collaborate compared to other places she'd been, like in Australia. And I think I reflected on that. I think that's true. They don't actually collaborate with each other, but they definitely interact with each other and they learn from each other. I mean, collaboration, many of them work for, more private companies that have their own proprietary models and things like that. So they're not sharing that kind of thing, but they're definitely communicating with each other. So this community of practice is a really good thing to tap into in terms of doing research. So I know I become acquainted with a number of these people. Like Steve said, I've been working with some of these people for 20 years. And tapping into this community for research is great, because you're getting people that are all interested in the same thing, but have a diversity of perspectives and insights. So it's a really rich way to collaborate. In addition, this is just the part of the larger community of practice for Colorado River management. And so they all have, a larger network that they can share, insights or any information that comes out of our collaboration with them. So that's been really, really a great way to do this kind of a project. Now, this is a subset of the people that we started working with at the beginning of the project. Interestingly, over this project, the set of people really shifted, and it was because, and if you notice who dropped out, some of the older folks retired. As I said, I've been at this 20 years now, so yeah, some people are now retiring. Some people, their jobs shifted, but a lot of younger folks joined from the same agencies, but turnover in people that are coming on board with different jobs. And filling the shoes of some of these other people. And so that's been a mixed blessing. In some ways, we lose that long-term relationship. In other ways, we're getting new insights and new perspectives. So it works both ways. So about this project, like I said, this Plausible Scenarios for Drought project kind of came about at the end of the first project that we had funded. At the second and final workshop, it was a 2-year project. We have workshops with our water managers once a year. So at the second and final workshop in November of 2016, we had this discussion. We had a lot of discussions, but one discussion was about plausible scenarios for future droughts. And I can remember Mark Waggy in particular from Denver Water was very interested in the more immediate planning horizon. He didn't really, for Denver Water, 50 years out, that's important, but really the immediate concern is what kind of drought can we expect in the next 10 to 15 years? So he said, what would a 1950s drought look like under current or warmer temperatures? And how would such a drought impact flow deficits? That was something that was like, that could be a plausible scenario. I mean, the projections for future conditions And all those span of projections and range of uncertainties is like, let's just what would happen if we had a 1950s drought and added warming? What would that look like? And we thought, well, we could do that. So when we wrote our second proposal, task number 1, if 20th century type droughts, i.e. the 1950s, under 21st century temperatures are the new normal for drought, how much such droughts impact upper Colorado River flow? So that was one of 5 tasks. So that's what I'm going to be talking about, plausible scenarios for future Colorado River drought, basically looking at instrumental period precipitation deficits plus warming. So we looked at Colorado River droughts. This is the estimates of natural flow from the Colorado River Basin for Lee's Ferry. So measure of all of the flow from the upper basin. This is in departure from average in million acre feet. And the yellow bars or yellow areas are showing the droughts. And this is using a definition that Reclamation has used, which is consecutive years below the long-term average broken by no more than 1 year of above average flow. And so you can see droughts in the 30s, the drought in the 50s, over the 60s, the drought that was really characterized by dry years in 1976 and 77, drought at the end of the 1980s into the 1990s, and the drought that started in 2000 and actually continues today by that definition. There's one drought that met the criteria for that we were given for drought in the 1940s. You can see that in the gray outline, and that it meets the criteria, but Reclamation has never recognized it. It just wasn't severe enough. It didn't have impact, so we didn't look at that one either. But these yellow outline droughts, these are the ones that we're looking at in terms of the droughts that we'll examine plus the warming. So in order to do these scenarios, we needed to have a model of Streamflow, which we could keep precipitation constant, keep it not constant, but keep it in the observed record values, and then add warming. And so we did this statistical model, which Steph McAfee developed. She published this in the paper in 2017, and we updated it for this study, where water streamflow is a function of cool season precipitation, that's October through April precipitation, warm season precipitation, May through September, May through July temperature, and the prior year flow. So she did a best subsets. This was the model that kind of met the criteria the best. It explains about 82% of the variance in the actual estimated natural flows. We're using, I should say, in the model, we were using monthly average temperature and total precipitation from gridded climate data from PRIM for the area of the basin above Lee's Ferry for 1907 to 2015. So that's the statistical model. What it doesn't do, it's a linear model, so it doesn't account for climate-induced changes in ET or in snowpack processes, shifts in seasonal or spatial precipitation patterns, ecological disturbance, or anthropogenically imposed land use changes. Doesn't go there. What it does do is that it provides a straightforward way to add temperature increases to 20th and 21st century precipitation deficits in order to produce and evaluate resulting streamflow. And that's what Mark Waggy and these other water managers said, yeah, that would be plausible. Just take that record, add warming, and see what you get. So we're not pretending this is like a be-all end-all model for projecting flows. This is a model for to meet a particular need and a particular parameters. So how good is the model? This is the observed record in gray and modeled record in black, and you can see it matches pretty well. As I said, the variance explained by the model is about 82%. So it's not perfect, but more importantly, how does it replicate the droughts that we'll be looking at? So this is showing scatter plots of all of those drought periods that I talked about, the average annual flow for all of those drought periods, the observed values on the x-axis, the modeled on the y, and then the line showing how close to that line they fall. So the 3 clustered there down at the bottom, those most severe droughts are the 1930s drought, the 1950s drought, and the 2000s drought. We do a really good job replicating those. We're a little bit wet for the 1960s drought, and for the 1970s drought, about a half an acre foot wet. And then we're overestimating the streamflow for the 1988 to 1996 drought by about 1 million acre feet. So that's one that is certainly we're not getting quite as good. So that's consider these biases as we go forward. So then we have our model. We're going to take instrumental period droughts. There's precipitation that is at warming. The warming is going to be plus 1 degree C to plus 4 degrees C. So adding 1, 2, 3, 4 degrees C and seeing what the streamflow looks like. And I'm not going to talk about, I'm going to talk about the droughts in particular, but overall, even with our simple linear model, that sort of at the end of the day, our decreases in flow with warming fall in line with all of the other analyses that have done not similar analysis, but I've looked at decreases in flow with warming out there in the literature. We had an 8% decrease in flow with each degree C of warming. And the end members are like 2.5, I think, from Hurling et al. And 13.5 from Nowak et al. So we're kind of in the middle. So even with our very simple methodology, we're in line with that in terms of the overall decrease in flow with warming. Okay, so here are the streamflow reductions with warming during those 6 periods of drought. So I'm showing you percent reduction for flow plus 1 degree C to flow plus 4 degrees C. And the bars, each of the bars is showing you the average annual flow reduction for each drought. So you can see the black, and I'll keep with this color scheme. So the black bars of the 1930s drought, the reduction in flow is the greatest for that drought. With warming, followed by the 1950s and the 2000s, which were about the same. And as I said, the red bar, that 1988 to 1996, we're underestimating the reduction, but the others are fairly close. So you can see that the reductions vary according to drought, and of course, the reductions increase with warming as might be expected. So it's about a reduction of maybe 5%. For 1 degree C warming, and a reduction of pretty much 30% with 4 degrees. So that's quite a bit of a reduction in flow with warming. The other thing we looked at was runoff efficiency, which is abbreviated RE. It's the percent of annual precipitation that becomes streamflow in the upper Colorado River Basin. So all of the precipitation that falls in the basin that runs into the river, all of the snow, all of the rain over the course of the water year, how much ends up in the river? On average, it's about 16%. So that's not a lot of water, but that's what it is. It's an arid landscape. There's a lot of evapotranspiration going on. And so as a consequence, temperature is really an important factor here. So we wanted to look at that. This is just a graphic that's showing percent runoff efficiency for the observed record. Plotted with May through July temperature in degrees C, and you can see it's a negative relationship. As temperatures are warmer, the runoff efficiency decreases. So that's the observed record. Now we add warming, we can see how that distribution shifts towards the warmer end of things, towards the lower runoff efficiency. That's 1 degree C, 2 degrees C, 3 degrees C, and 4 degrees C. So the shifts are predictable. What it's a little harder to see in this graphic is that the slope is actually changing too. So we're seeing as temperatures increase that the slope of that relationship becomes steeper as well. So with 1 degree of warming, the runoff efficiency decreases about 1.6% per degree C. And at the extreme end with 4 degrees of warming, that decreases nearly 2%. So if we're talking about an average runoff efficiency of 16%, we're losing nearly 2% of that when we get up to the upper end of that warming at 4 degrees C. So in terms of our droughts and runoff efficiency, this is showing the percent runoff efficiency, and then for the observed flow, the model flow, and for the flow plus warming. So I'm showing you the observed and the modeled to again compare the modeled results to the observed record. And you can see that the lowest values of runoff efficiency are for the 1930s drought, the 2000s drought, the 1988 to 86 drought, 88 to 96 drought. The highest runoff efficiency for these droughts is for the 1950s and the 1970s drought. And we replicate that fairly well in the model flow, except for that 1988 to 1996 drought, where we're wet on that. And so you can see how those, the distribution among the droughts kind of adjusts, kind of varies as we get increasing warming, and also how that runoff efficiency drops. So again, overall, on average, the runoff efficiency is about 16%. And during the droughts, the observed droughts, it varies between about 14% and 15%. But when we get to 4 degrees of warming, we're down about a 10% runoff efficiency, which is, that's quite a reduction in runoff efficiency. That's 10% of the precipitation that falls in the basin ends up in the river. And here we are again, not adjusting the precipitation at all. In terms of projections for precipitation, that's really uncertain in this basin. We're not sure if it's going to increase or decrease or stay the same. Okay, so getting back to Mark Waggy's question, what does the 1950s drought look like with warming? Here are the flow reductions with warming in million acre feet. Again, well, average annual flow is about 14.8 million acre feet. The 1950s average was something like, I think it was about 13 million acre feet, and then decreasing with warming to about 8 million acre feet. And then here's the percent reduction. So we're seeing a reduction of about 5% for 1 degree of warming, and about 35% with 4 degrees of warming. So what about runoff efficiency? The 1950s drought was a relatively cool drought, if I can say that. And so I'll show you the comparison with the 1930s in a minute, but the 1950s runoff efficiency was not that, was just slightly less than the average runoff efficiency. So it's close to 16, 15 something. But that runoff efficiency dropped to about 10% with 4 degrees of warming. Here's what the 1930s drought runoff efficiency looks like compared to the 1950s. And so about a half a degree warmer on average. The 1930s drought was compared to the 1950s drought, and you can see the corresponding decreases in runoff efficiency with that warming. So we thought those were pretty interesting results, but we weren't really sure if they would be meaningful to our water manager partners. And so at the end of the first year, we brought these results to our partners. Our typical workshop was that we would say, here's a little bit about the project again. Here's what we've done. What do you think? What should we do next? And our workshops basically were about 6 hours. So we had time for lots of discussion. And so for this workshop, we were looking for some guidance, like, are these results meaningful, or can we do something else? And the discussion kind of evolved around thresholds or triggers in Streamflow that could impact the Colorado River system. And so I can remember Lorna Cates, who's with Denver Water, saying, what should we be looking for? What do these reductions mean? When should we be worried? There's a term that's been coming up more frequently in this community, signposts. What kind of signposts should we look for? What should we be aware of when we're evaluating these kinds of scenarios? So Ken Nowak with Bureau of Reclamation suggested that we consider vulnerability thresholds that were in Reclamation's Basin Study Technical Report G. Now, the Bureau of Reclamation has a program called the Basin Water Supply and Demand Study, and they do these studies for all of the basins that they have reservoir operations. So all of the major basins in the Western United States have these basin studies. And the basin studies are very comprehensive studies done with Reclamation and Reclamation's non-federal partners that examine the water supply, the water demand, projections for the future. And the one for the Colorado River was done in 2012. And along with it was this technical report G, system reliability analysis and evaluation of options and strategies. And Ken said, take a look at table G3-2. So we said, okay, we'll do that. And that table had some thresholds that we could apply to our scenarios, our warming scenarios for stream flow. So we did that. we applied those thresholds. We had some graphics. We still were not exactly sure what they meant and if they were meaningful. So at our second and final workshop with water managers in November of 2019, we sort of went, well, what should we do with this? And among the group of people, which at this point really had evolved. And so we had a number of people like Mark Waggy was no longer with us. He was the one that sort of suggested this study. I mean, there's agreement that it was important, but this is his suggestion initially. Some other folks had left, some new people had arrived, or like, what's going on here? So we had this sort of a little bit of a disconnect, but we had a good discussion about vulnerability assessment and how we might make our results more meaningful. Rebecca Smith was someone who was new to reclamation. She was hired between the two studies. Her position was to act as a liaison between the researchers who were doing work that was relevant to the upper Colorado River Basin and people like Jim Prairie, who worked for reclamation. His job was to kind of take science and research that seemed like it was applicable and introduce it to the guys that did operations. And so we were so lucky that she stepped in there because she had actually studied this report, technical report G, and understood what was behind it. And so she, at this point, Jim said, Rebecca knows all about this. She can help you with this. So our discussion was about this vulnerability assessment and how best to interpret and present the results highlighted in this technical report G assessment. So what I want to talk about is that assessment and how we came to understand it and how we came to use it to highlight some of our results. So this is a schematic of the assessment process. It starts with scenarios. So water supply, water demand, and policy scenarios. For the supply scenarios, it included observed streamflow, paleoclimatic reconstructions of streamflow of a couple different flavors, and downscale GCM projections of streamflow. The demand scenarios included ones that adjusted growth, made adjustments for development and for human environment values, so in stream flows. And then they had two future operation scenarios. One is the current interim guidelines that were started in 2007. And then the other operation scenario were the previous operating guidelines. And so those were inputs, supply, demand, and policy into the Colorado River Simulation System Model, CRSS, which is Reclamation's long-term streamflow model. The outputs were streamflow, reservoir operations, releases, water deliveries, et cetera, lots of different things coming out of there. And the outputs then were evaluated with this vulnerability assessment. Okay, now the vulnerability assessment has three parts. It has indicator metrics, it has vulnerability thresholds, and vulnerable conditions. So I'm going to talk about the three of those and give you sort of examples of what they look like. So an indicator metric is a quantitative variable that captures performance in important categories of system reliability. So these are the 6 categories, resource categories: water delivery, electric power, recreation, ecological, water quality, and flood control. And each one of these has indicator metrics. So metrics that people are keeping an eye on that are important for doing, for example, water delivery, like upper basin storage, leaf area deficit, Lake Mead pool elevations. So those are the indicator metrics, and I'm going to be talking about water delivery. Okay, the next one is vulnerability thresholds. And these are identified for each indicator metric to define unacceptable performance, i.e. a vulnerable state where you don't want to go. So for the water delivery, for each of the indicator metrics, a vulnerability threshold is stated. Now these thresholds were, I don't want to say they were negotiated, but it seems like there was a team of people working on these, including partner agencies and experts, to determine what these thresholds should be. And some of them are directly tied to compact requirements, and some of them are based on expert opinion, like for upper basin shortage. The threshold not to be crossed that they determined was shortages exceeding 25% of requested depletions in any one year. For leaf area deficit, it was running 10-year sum of deliveries that fall below 75 million acre feet in any one month. So 75 million acre feet is tied to the compact allocation over 10 years. So some of them are directly tied to compact specifications, and some of them are tied to other kinds of thresholds and decisions that were discussed in the negotiation of these thresholds. Okay, then finally we have vulnerable conditions. So those are the combination of uncertain future conditions identified as likely to cause vulnerable thresholds to be violated. So this is where things got a little murky, and Rebecca really helped out. Vulnerable conditions were determined based on all the scenarios of all the runs of the flow scenarios and a statistical technique called the Patient Rule Induction Method, PRIM. I don't know anything about PRIM. I tried to get a sort of a plain English translation for what it is, and I couldn't come up with anything, so I can't explain it. This part of the study was done by the RAND Corporation. So what they were trying to do was to identify a small set of conditions that could be applied to many of the metrics, so that you could evaluate them using the same set of characters. So they determined that these vulnerable conditions were found to be best characterized by three aspects of Colorado River stream flow at least vary: long-term minimum water year flow, long-term average water year flow, and the driest 8-year period. So these are all things that we could generate with our scenarios of stream flow with warming. Okay, so I'm going to talk about a couple of ways we applied these vulnerable conditions to the thresholds. So again, I'm talking about water delivery resource category. I'm looking at two indicator metrics: upper basin shortage and leaf area deficit, the associated vulnerability threshold, and the vulnerable condition description, which is different for each of these. So for the upper basin shortage, the vulnerable condition was 1 year minimum annual natural flow below 8.3 million acre feet. Now this one is easy to understand. 8.3 million acre feet is what the upper basin needs to pass down to the lower basin of Mexico every year. So it's the 7.5 million acre feet that goes to the lower basin, and then half of the allocation to Mexico, which is 1.5 million acre feet. So half of that plus 7.5 million acre feet is 8.3. So that one's easy to understand. The leaf area deficit vulnerable conditions are a combination of two different metrics: annual mean natural flow less than 13.8 million acre feet, and the driest 8-year drought less than 11.2. So that's what their algorithm using that PRIM method came up with for this vulnerability threshold for leaf area deficit. So taking that, we evaluated our stream flow scenarios with warming. And this is what we got for upper basin shortage vulnerable conditions. Again, that's the 1 year minimum annual flow below 8.3 million acre feet. So for the observed and modeled flow without warming, it was between 3 and 4 years. So just without any warming at all, there's a very small number of years that meet that condition where we don't really want to go. As you add warming, as you might expect, we get more and more of those years. And in fact, with 4 degrees of warming, we get about 35 years where the flow is below 8.3 million acre feet. So that one's pretty straightforward. And I should say, to get back to Mark Waddy's question, during the 1950s period of drought, we didn't see any of those years until we got 3 degrees of warming. And then there were 2 years, 1954, 1956. And with 4 degrees of warming, 3 years fell below that threshold. Okay, so here's the one for leaf area deficit, vulnerable conditions. Again, it's a combination of 2 conditions. So on the x-axis, that's long-term average flow. And I've marked where 13.8 million acre feet is. That's the threshold where we don't want to go. And then for the 8-year period mean, that's on the y-axis, and we don't want to go below 11.2 million acre feet. So that sort of tan area is the area of vulnerable conditions. And then what I've plotted are all the scenarios from no increase in temperature to increase of 4 degrees. And the dots all represent an 8-year flow average. So they're running 8-year means. And as you can see, as we get into more warming conditions, we have a larger number, a higher percent of 8-year periods that meet both of those conditions, from just 4 8-year periods with 1 degree C, warming, and up to, I think it's like 68% of the 8-year periods with 4 degrees of warming. So that kind of gives you an idea of, as you're moving into these conditions, as the temperatures are warming, the likelihood of meeting both of these conditions, which would impact the leaf area deficit. So in terms of project outputs, we actually started working with Rebecca fairly closely after the end of the project. So Rebecca joined us in a paper. She was second author, and Paul Miller, also, who was from the Colorado River Basin Forecast Center, was a co-author on this paper that we published that has everything that I've talked about. In addition to that publication, we put out a fact sheet that Paul and Rebecca helped us with, a 3-page fact sheet that we shared with all of our partners. We've not really heard from anybody since then. And so in terms of project outcomes, what are people doing with this? Did this make an impression? I had an acknowledgement from a couple people when I sent it out, but I don't really know if or how people are using this information. Now, the RAND part of the technical report G, these vulnerable conditions were meant to be used as a signpost for crossing system vulnerability thresholds. So our results suggest that warming would prompt those thresholds to be crossed with increasing frequency. Now, I've plotted the current or the updated record of Colorado River flow at Lee's Ferry. So this is actually 1906 to 2021, the last 2 years are estimates from reclamation. I plotted in a blue line the 13.8 million acre feet threshold. And you can see that's crossed in the instrumental record. And then there's the 8-year running mean, which hasn't really been crossed. And so in theory, you could be watching those 8-year running means along with the average annual flow and sort of see where you might be heading into that vulnerable condition territory. But I don't know if this is being used. So for us, the project formally ended, I guess it's been a little more than a year now, but we're still working on what we really set out to do, or one of the things we really set out to do, which is we acknowledge that the instrumental period of record is just a subset of the drought events that have occurred over past centuries. And so well, it's a good place to start, and especially for water managers who, like Mark Waggy said, give me a 1950s drought and add warming. We know that there have been droughts in the past that have been longer, more severe. This is the record of Colorado River, at least for reconstructions from 1766 to 2005 that Dave Miko led. Came out in 2007, and all of the droughts defined the same way that we defined the instrumental period droughts, and then the 20th century droughts shown there in the red box. And so we've got a wide variety of droughts shown in this record. So our next step, actually we're in the process of doing this, is to take the paleoclimatic record droughts and add warming. And this is not a trivial exercise. Greg McCabe and Steph McAfee and Greg Peterson and I, mostly Steph and Greg McCabe, have been working hard on this for a couple of years now, delayed a little bit by COVID. But in order to do this, what we need to do is model Streamflow using paleoclimatic reconstruction. So reconstructions of precipitation and temperature, which need to be spatially and temporally disaggregated to provide input to a water balance model. So that's been the really tricky part, which Steph and Greg have pulled off. And what I'm showing you here are an ensemble of runs from that process, and then the instrumental record in the black line. So we've demonstrated that we can actually do this. And now it's a matter of figuring out how to analyze these droughts and add warming and see what they look like. So that's our next step. Hopefully, I mean, they have the interest in the water managers. We're not still engaged with them as much, but I anticipate that when we get to this point, we'll have some folks that are interested in this, at least I hope. So that's the end of my story. it's you know, Steve kind of like touted me as I'm doing this successfully and I'm a model for others. And it's like, it's not easy to do this kind of work. And a lot of times we're not really sure the impact that we have. But I do know that we appreciate our water manager partners. We have a good relationship. They're interested in what we're doing. I have to say that most of the time, if you ask them how they were using this information that they're getting from our work, they would go, well, you know, it would be hard to articulate it exactly, but I think that it's being absorbed, it's raising their awareness, it's information that they have in the back of their minds as they move ahead with the work that they do. So that's it. Thank you for listening, and I'd be happy to take any questions.
Thanks so much, Connie. We do have a few questions already, actually. So this first question is from Juliet McKenna. She asked that the definition of drought is based on comparison to what average? So historical record or 30-year, et cetera.
Good question. Yeah, that's based on the instrumental period average. And I should say that, you know, initially when we did this, reclamation was like, well, what happens if you do a definition where it's consecutive years below the long-term mean with broken by 2 years? So we played, you know, it's a definition. There's lots of definitions. That's what we use. Not to say you couldn't do this a different way.
Sure. And then follow up to that, is that definition applied to streamflow and precipitation records, and on what scale?
It's applied. That was to establish the droughts that we looked at. So it was applied to the streamflow record only. And then we used those years. Once we defined those years in the streamflow record, we stuck to those years and looked at the temperature and precipitation values from the model for those years. So the droughts were based specifically on the streamflow record, based on, you know, the average for the streamflow record, 2007, in this case, 2007 to 2015.
This next question is from Steve. Do the runoff efficiency estimates take into account temperature effects on whether precipitation comes as rain or snow? Or put another way, does snowpack reduction have a negative amplifier effect on runoff efficiency?
Runoff efficiency, it's interesting. I'll give you a little background. I never knew about runoff efficiency until one of our workshops where our initial interest and that of the water manager was the effect of temperature on streamflow. And so we were doing different things to show that. In one case, we showed the difference between streamflow and precipitation. And this guy said, oh, that's runoff efficiency. And we're like, what? Runoff efficiency? Oh, okay, that's what it is. And we're using the definition that they use, which is the volume of streamflow. Is it the volume of streamflow? The volume of streamflow, the ratio of the volume of streamflow to the volume of precipitation over the course of the water year for the upper basin. So that's a specific definition. It's very simple, very straightforward. You know, there's what goes into runoff efficiency is another question for sure. I mean, we think a lot of it is evapotranspiration, but certainly you've got lots going on with the snowpack that plays into that. So it's runoff efficiency. Actually, that was something we were we were going to look into more closely, and we didn't get around to it. It's a really interesting question.
Well, this question is tied to this a little bit about evapotranspiration. So as you did not look at the impact on evapotranspiration and snowpack, were you assuming that these impacts would be subsumed in the results?
Not sure what that means. Want to elaborate?
If I can elaborate, maybe Susanna can, if she's still on. And I can even allow her to talk if she'd like. We can skip to the next question, Susanna, if you want to type it either in the chat or the Q&A, or let me know and I can allow you to talk too if you'd like to speak a question. So this one's from Liz Payton. How far did your disaggregation of paleo flows go in terms of spatial resolution?
Spatial resolution. Well, we looked at the upper Colorado River Basin, and Greg McCabe was, we disaggregated the paleo data to match the PRISM grid So a 4-kilometer grid. And then Greg actually was developing water balance models for the Huck 8 level areas and then combining those. And actually that turned out to be very, very computationally intensive. And I think he might have scaled it to a larger scale at some point. I'm not sure where he's at on that, but we did run into some long computation times on that, but it probably didn't need to be that fun. We actually did some sub-basin analysis to evaluate the model results, and we didn't do as well as the entire basin. And so we ended up sticking with the entire basin, even though we're starting with a pretty fine resolution of data.
Okay. Liz says thanks.
You're welcome.
Next question. For planning purposes, can we yet define a quote unquote worst case planning scenario?
Well, I mean, I guess it depends kind of in your planning context. Every, different agencies might have different vulnerabilities. In terms of, just looking at Streamflow, I mean, that's one of the things that we're getting at with the paleo record is, can we take the worst Streamflow drought in the paleo record, which is based on not elevated temperatures, they might be warmer, but certainly not as warm as they are now. Take that record, that part of the record, and add warming. And that presumably could be a worst case scenario. We did a paper in 2010 about a worst case scenario in the paleo record, but just by itself. And we said, well, this is the worst, a medieval period drought is the worst case scenario, but of course temperatures are warmer now. So, we're taking that to the next step at this point, going, let's take that worst medieval period drought and add warming and see what that looks like. Assuming that medieval kind of drought could occur in the future, because as far as we know, there's no reason those couldn't occur in the future, but add warming and see what that looks like. And that would be a worst case scenario. But we're not there yet, but we're getting there.
Okay, so Susanna clarified her question a little bit. Evapotranspiration and snowpack are major determinants of streamflow impacts of higher temperatures. So do your model results capture these impacts in terms of total impacts?
Like I said, this is very, very simple. We're only looking at temperature, precipitation, and streamflow. So we're not getting in, we're not even analyzing it on a seasonal scale. So it's all integrated in there. We couldn't tease out in this particular exercise, we couldn't tease out those different impacts.
Thanks. Next question. This is from Chris Fullerton. So you mentioned the turnover in water managers during the engagement process. Evidence suggests a significant number of baby boomer water managers, or water buffaloes, are approaching retirement. So based on your experience, can you suggest strategies for minimizing disengagement from the science by next gen water managers? That's a good question.
It is a good question. And, I feel, this last project, it really hit me in the last meeting that we had, that half of the people that were in the room hadn't been with us on this journey. And so they weren't really getting what we were doing. And at this point, I don't have any funded research to pick up with those folks again, but ideally you would continue on working with those people, bringing on the new people, bringing them up to speed, getting their new perspectives, getting their buy-in, and they're building those relationships again. So in a perfect world, that would happen, and my younger colleagues like Steph McAfee would be taking my place as I, in a few years retire. It's sort of a generational thing and a trust building thing. So it's kind of an interesting thing to see the effects of being around for a while and some of your closest collaborators retiring, and then, bringing on the younger people. Some of them are, like Rebecca is like, thank God for Rebecca, she's great. But others are like, I felt bad. The Denver water people, instead of Mark Waggy, I had, I can't remember his name now, but we'd never met. He showed up in Salt Lake City and he was like a little baffled because he had no history in the project. Right. And I couldn't start over, at the beginning we did review what the project was about in the background, but we just couldn't start from the beginning. And so I feel bad that and I tried to follow up and said, here's some more information, but ideally we should have another workshop and get those people up to speed and keep building those relationships. So I don't have a good answer for that problem, other than it would be great to have some kind of a program that, and I'm not saying CASC is not doing a good job, because it's one of the few programs that funds this kind of research, right? But it would be great to have more continuity in these projects, so you could continue to build these important relationships.
Yeah, and maybe that's something we should think about more. I know, and with the federal agencies, turnover, even not just retirement, right? Turnover can be tough. We've been working with the Park Service.
Yes.
They have details at different, just for like 6-month periods. So you work with someone for 6 months and then they go off to another park. And so I don't know if I have a good answer either. I know we've been trying to put together like product fact sheets, little things that can try and keep people, bring them up to speed if they need to be, come into different projects. But it's tough. Steve, did you want to add to that?
Yeah, this is a really important issue of this whole continuity. And we haven't given nearly enough thought to, we invest a lot in not only in the science, but in building these relationships and partnerships. And of course, they're ephemeral because people are turning over with retirement or moving on to taking on different jobs. So this is worth a conversation about how we most effectively maintain that continuity of community and conversation. And I'd be happy to talk with Connie and Greg and others about how we might try to solve that problem. Is it a matter of just doing more convenings and workshops to try to incorporate earlier career people as they come on, and maybe bring in some of the recent retirees to help brief them and explain the context and the value of this. I'm not really sure. I think this is an important issue to be thinking about, though.
Yeah, there's no perfect answer, but there's certainly things that could be tried, and maybe some things to be put into place to help. Yeah.
Well, that's all of our questions. I guess we'll give people another minute or two if there are any more, and then we can adjourn early. I like your last photo here, Connie. That's is that near Lake Mead? Or is this?
It's someplace, I'm not sure exactly where it is. It's one of those that I grabbed off of the internet because it had a nice bathtub ring. I think it's probably, Lake Mead or Lake Powell. I should probably have the credit there, but I don't.
Oh, another question. Can you explain in lay terms how we use this information to alter water use practices?
That's a good question. It's a little bit out of my area in terms of what I might recommend, but I think, there's some specific things if you're a water manager that, again, watching those triggers, those thresholds, we're going through a drought now. It looks like we're not hitting an 8-year running average that's going to hit that specific threshold, but certainly all signs indicate that warming is going to result in less water and less runoff efficiency. And so thinking about ways to conserve water now rather than later is probably a good approach. I'm sorry, I'm generalizing, but it's going to be different for every agency.
Okay. Well, if we don't have any more questions, thank you everybody very much for joining us today. I'm going to paste in the chat again the link to our past webinar recordings, and this recording will also be posted on there by Monday. And then I've also included the link to our podcast. Again, on Wednesday, the episode is on snowpack, streamflow, and drought with Brad Udall and Adrian Harpold. So it's very relevant to this topic. And Brad touches on the impending shortage declaration that's expected. So yeah, thank you again. And thank you, Connie, for
All right.
time today. We appreciate it.
Thanks for joining. So I can't see everybody.
Okay.